So let's talk about some more sorting. We'll look at some more first order functions. And we're going to start talking about recursion today. So the lecture question is going to hit that last point, recursion. This is the first time I'm asking you to write a recursive method. So for this question, this is going to follow the same rules as the next round of homeworks are going to follow, in that you can't use the keyword var. You cannot create a variable for this assignment. And the expected solution, the expected way to get around this restriction is, this is my way of trying to force you to use recursion. And hopefully that's successful. If it's not, I'll start adding more restrictions and force you into that recursive solution and that functional programming way of thinking. So for this, the question is simple enough, especially if you heard of these before, is write a method that computes the nth Fibonacci number. So I assume most of you have seen Fibonacci numbers. If you haven't, the sequence starts with 1 and 1, and then each number after that is computed by summing the previous two numbers. So 1 plus 1, 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. So as an iterative solution, this is straightforward. You start with 1 and 1, and then just keep summing up all the values until you get to the number that you're looking for, the index that you're looking for. So we want to be able to write this as a recursive method for the homework assignment, or for the lecture question. So how do we write a recursive method? And that's what we'll talk about the next few days, starting at the end of today, and then all of Friday is going to be recursive. Yes?
Is this going to follow the same sort of procedure with the object-oriented programming lecture questions where it can't be in the same file as the...
Yes. Okay. Yeah. So if there's a var anywhere in your code, it's not going to work. It's not going to compile. So for this one, just submit the file where this is. So it follows those same rules. Make sure nowhere in your submission do you have code that uses the keyword var. And you can expect this for the rest of the 4 following lecture questions as well. We're going to ban var, especially for the immutability ones. That makes sense because with var you really don't have immutability. But also the recursive ones, I'm going to use these recursive ones. And then Monday we're going to dive headfirst into applications of first order functions, so that we're going to also ban var for those. So let's take a look at how we're going to do this. For most of this lecture, we'll talk about sorting, and at the end, I got some tips on how to start thinking about writing recursive methods. All right, so last time we saw selection sort. We saw that it was very inefficient. It works, but as we know from 115, it's an n-squared algorithm, meaning there are, if you have an input of size n elements in the data structure, it's going to take an order of magnitude equal to n squared, not exactly n squared, but n squared times some constant number of operations to be able to compute that. So we want to do better, and we want to figure out the number of steps by the complexity by counting the number of steps. And steps, it's a little bit arbitrary, but we're going to use these as any basic operations like addition, subtraction, multiplication, division, Boolean operators, etc. Val is accepted for the assignment. You can use val, but no var. So var, with a var, your values can change. I don't want any values changing for these assignments. If you could use var, for example, you just throw that in a loop and have a var that's going to be your accumulator and use that accumulator pattern from 115. I'm saying you can't use the accumulator pattern now. What's another approach that we can use for this? So you can use val and create those constant values, but nothing that can change. So let's count the number of steps and count them asymptotically, meaning as long as it's the same order of magnitude as whatever we say, then it's okay. So if we have some input of size n, and the operation, the algorithm, the method that we have takes O of n steps, what we're saying is that it takes n times some constant and potentially even plus some constant number of steps to be able to execute. So in O of n algorithm, it's going to take n, either could be n times 100 steps for each input. It could be n divided by 1,000. but that would still be O of n, as long as it's linear, as we say, in n, n times some constant plus some constant, it's going to be O of n runtime. So a selection sort, let's do just a high-level runtime analysis. We won't focus too much on runtime analyses in this course, but believe me, you will get a healthy dose of runtime analysis in 250. 250 is mostly all about runtime analysis and designing algorithms that work on your data structures to be able to get lower runtimes, lower asymptotic runtimes. For 116, we're just going to give a quick overview of what a runtime analysis looks like. So for this selection sort, we look at our outer loop. This iterates over the indices of my data structure, and we always measure n as the size of the input. So if the input is a data structure, n is the number of elements in that data structure. So if the size of our data structure is n and we're iterating over all the indices of that data structure, this loop is executing n times. And this is actually exactly n, it's not even asymptotically n. This loops n times, so we're going to say that's an O of n loop. This loop runs O of n times. It happens to run exactly n times for this case. Then we look at whatever's inside that loop, and whatever the runtime is inside that loop, we multiply that by n times for the loop, and that's our total runtime of that outer loop, which in this case is the total runtime of our entire algorithm. So we look at this loop. This loop is also running over the size of the data structure, but it starts at I, our current index, and not the total size of the algorithm. So it's a little more work to do for the purposes of this class. I'll show the math in a few slides, but for now, let's just say, well, the worst case that can happen is n. If I is 1, I is going to be 1 at least one time. So this is going to be another O of n loop. It's not always exactly n, but we're still going to get an O of n runtime out of this inner loop. So we have an O of n loop times an O of n loop. We're going to get an overall n squared runtime out of this algorithm. So that's how we get our overall n squared. Now I mentioned this before, a while ago also, we actually have at least n cubed, and I keep saying at least, but I can analyze this pretty quick. Yeah, we have an n cubed total algorithm. But last time I said it might have been n to the 4th. Looks like it's n cubed to actually run this because apply of j is going to be an O of j runtime algorithm, and j can be as high as n. So I have another O of n right here inside my inner loop. So I actually end up, just by this implementation, an n cubed algorithm. But that's only because I'm being sloppy about the way I manage my data structures. If data were an array and I had random access, this would be an O of 1 operation, and I would be down to the theoretical n squared runtime of the algorithm itself instead of an n cubed implementation of an n squared algorithm. So there are cases where you can have an n squared algorithm or even an n log n algorithm like we'll see in merge sort and implement it poorly such that you don't actually get that n log n runtime. So we always have to be aware of our implementation even when we're implementing an efficient algorithm. And the reason I want to highlight that and the reason I leave that in there, why I have that in there, is because we'll be talking about linked lists after spring break. I want to make sure we're aware of some of the inefficiencies of linked lists, and then when I talk about linked lists, I'll be like, hey, remember when we had that selection sort that was awful? Let's talk about why that was awful. So we'll table that for now and talk about it when we come back and talk about linked lists after spring break. So I mentioned that inner loop was O of n, even though it's not always n. But let's analyze this a little bit more and break apart the entire algorithm to look at the whole runtime of that. That inner loop is going to run n times the very first time we hit. We're going to find what belongs in that first index. So we're going to have to compare with every single element. Every single element gets compared at least once in that runtime, in that inner loop. So we're going to have n. And then once we're looking at the second index, we're going to end up doing n minus 1 comparisons. For the next index, we're going to do n minus 2 comparisons, so on and so forth. And we have to sum up all those down to 2 and 1 for the last few runs. And when we evaluate this series, we're going to get n squared over 2 plus n over 2. n squared over 2, well, that's just n squared times a constant. We can ignore the lower order terms, and we have our O of n squared runtime algorithm. So even if we don't do that hand wavy, well, worst case it's n squared, or worst case it's n, we can look at the math and actually verify this is, in fact, an n squared runtime algorithm. All right, so we can do better. You also briefly saw merge sort in 115, unless they cut that content. We show it very quickly in half a lecture, selection, sort, and merge sort all in one lecture. So it came and went really quick, but let's look a little deeper into merge sort and see how it got its n log n runtime to be able to sort using comparison sort. So merge sort on a high level, if there's less than 2 elements, just return that list. If it's a list with 1 element, that's already sorted. If it's an empty list with no elements, well, that's already sorted too. So there's no work to do, we're just going to return it. And this is going to be an important part when we're talking about recursion in general. This is what we call our base case, where it's some trivial case where the answer is just very obvious, we can just return it right away. So our base case here is if we have less than 2 elements, the list is already sorted, just return it. We're already done, there's no work to be done, no work to be computed. If the input is not already sorted, then we're actually going to have to sort it. We're going to have to do some work here. So for merge sort, we're going to use what's called the divide and conquer approach. We're going to split the input list into 2 halves, recursively call merge sort on each half. We're going to get the return values of those merge sort calls, which are going to be those values but in sorted lists. And then we're going to merge those 2 lists together. So once our recursive calls come back, which through the magic of recursion, we're just going to assume that it works and that those are sorted, even though we're calling the same algorithm, the same method that we're writing. And then we're going to merge those 2 sorted lists into one single sorted list, which is a much simpler problem to solve than just sorting in general. So combining 2 sorted lists, very much simpler than sorting one larger list. So to visualize this a little bit, if we're trying to sort this list, which I conveniently have a power of 2 number of elements, so everything breaks down neatly on the slide. So we're going to take this list, break it into 2 halves, and recursively call merge sort on each half. Now for each of those halves, the algorithm is going to say, is this list, the length of this list less than 2? Well, no, so we're going to make 2 more recursive calls for each of these recursive calls. So I call merge sort the same method on this half, and it says, okay, I'm going to split this in half and call merge sort on each half. It's going to start computing on this half and say, well, this length isn't less than 2 either. I can't do anything with this. I'm just going to call merge sort on each half of this as well. Calls merge sort on 51 and 1. This recursive call is going to call merge sort on 119, and same on the other side. So we end up with 8 recursive calls after all the recursion goes down to the base cases. So nothing actually happened yet. We just made a bunch of recursive calls. So we just made a bunch of recursive calls. And now we want to combine the lists. And in a few slides, I'll talk about exactly how we're going to combine these lists. For now, let's just say we have code that can combine 2 sorted lists into one larger sorted list with all the same elements. But once these recursive calls start coming back, I have 51. How do we merge sort 51? Length is less than 2, therefore it's already sorted. Just return it. Same with 1. Just return it. The list containing only 1 element with the value 1 is already sorted. Just return it. So now, with this recursive call, now that the recursive calls from this one came back, and I have 2 sorted lists, I have the task of combining these 2 lists. So I have to combine the list with just 51 and the list with just 1. Combine those into this list of size 2 with 1 and 51. This recursive call does the same thing. It gets its return values back from these recursive calls, combines those 2 lists into this list with 19 and 100. Now this recursive call that was waiting for those two recursive calls to come back gets these two sorted lists and organizes them into one list with all the same values. It takes 1, 19, 51, and 100 and combines them into a larger list. And then our top level call was waiting for these two to come back. The same thing happens on this side, gets these two sorted lists, and then takes all the values as needed in sorted order, combines those two lists. So we make our recursive calls, and it seems like we're just assuming that the algorithm that we're currently writing already works. But this is how it's starting to work. We can see it starting to work if we break out the recursions. Once we make recursive calls until we reach the base cases, once we reach the base case, we start getting return values. We start deleting stacks off the frames off the stack and start returning. And then our algorithm is tasked with combining two sorted lists. That kind of becomes the crux of what we have left to do after the recursion is doing its part. So that looks like this. The top level algorithm will go into the merge method. We haven't seen that yet. There's a little bit more complexity, just some bookkeeping and stuff that has to be done there. That has to get done there. But the top level of this algorithm isn't too crazy, not too much code here. We're going to take a comparator just like we did with selection sort. So we know how to compare elements. We're going to use a type parameter so we can sort anything. We don't care what we're sorting. We're just going to be sorting based on a comparator. Doesn't matter what we're sorting, doesn't matter how we're sorting them. We're just sorting based on a comparator. We get our data. If it's length less than 2, just return it. Else, split this data in half, make the two recursive calls, and I'm taking advantage, this is one case where I do want integer division. I'm taking advantage of integer division, so if the list is an odd length, I'm going to get a nice split that's as even as possible, just because the integer division is going to round down. If this is a list of length 5, this mid is going to be 2, then I'm going to have 0 to 2, and then non-inclusive, and then 2 to 4, or 2 to, I pointed to the wrong things, split at mid. So I'm splitting right there, getting the left and right, then calling merge sort on those two halves. 0 to 2, and then exclusive, so just 0 and 1 indices for the left list, and then 2, 3, and 4 indices in the right list. I'll get that split without having to worry about odd and even, the way I'm taking advantage of integer division here. So make the two recursive calls, assume that these return sorted lists with the same values of the lists that I gave it, and then merge those two lists based on this comparator that we're given. So the top level merge sort, not too crazy, but we are using this crazy thing called recursion in this, which is going to take us a little while to digest and see what's going on with the recursion. So let's take a look at the runtime of this and see where we actually get this n log n, where we come up with this, instead of just saying that it's n log n. So when we start with a list of size n, each level of the recursion that we go down, when we look at our first recursion, each level that we go down is going to split the input size in half and double the number of inputs. So for example, if I go down one level, I'm going to split this 8 into 2 lists of size 4, and then 4 lists of size 2, and then 8 lists of size 1. Each time we go down this level, if we visualize this kind of as a tree and going down this recursive tree. So each time we go down, we're going to divide by 2 and have twice as many lists. So if I'm at level I, I'm going to have lists of size n over 2 to the I. So if I go down 3 layers, like I did in the other recursion, we're going to have n over 8. And in our example, we'd be down to our base case. So our question is, in general, for any input of size n, how long does it take to get to our base case of size 1, well, how long is it going to take? How many levels of this recursion is it going to take to be able to get to that base case and start being able to return up the recursion? So how many levels do we have in this tree is what I want to ask. And if we solve this for I, we're going to have I equals log of n. We have log n levels to that recursion, and we really get to see the power of exponentiation and the power of logarithms. If we have a very large input, it doesn't really take that many levels of that to go down the tree. With 8, you don't really see it too much. 8, it took us 3 levels to get down to the bottom. But if we had 1,000,000 elements, how many layers are in that tree to get down to the bottom? It's only 20 to be able to get all the way down to our base case. Logarithms are extremely powerful, and logarithms are just the other side of exponentiation. Somebody says it grows exponentially. It's a ridiculous great growth rate. Of course, these days people say that even if it's not actually exponential, but in computer science, we have actual exponential growth in a lot of things, a lot of things that we'll analyze. So log n levels to our recursion. And if we merge, if each level of that recursion, if I'm going for that n log n runtime, each level, I'm restricted to only O of n work at each level. So if we can merge these lists in O of n time, we'll actually get our n log n runtime. So if we want this n log n runtime, which we do, we're going to have to merge in linear time. That's our new task to get this runtime. So if we merge that, now of course we're in a way kind of tasked with sorting. We have n data elements, and we want to sort them. We want to return a sorted list with all those elements, which we can't do in faster than n log n. So we have to take advantage of the structure we're given, which is the fact that these two lists are already sorted. And we have two already sorted lists, and we want to combine them into one sorted list with all of the elements from both of the lists. So we're going to take advantage of that, and that's how we're going to be able to merge in linear time. So yeah, I do want to read that. So the way we'll do this is start by comparing the first element in each list, and whichever one is less, copy that to the output list and advance that pointer. On a high level, that's the whole algorithm. And then there's a little bit extra. When we reach the end of one of the lists, copy everything that's left in the other one to the other side. So if we're tasked with merging these two lists, for example, we're going to be looking at the first element in each list, and we're going to compare them. Is 1 less than 2? Yes, 1 is less than 2. So 1 is going to go here. We know that 1 is going to be the lowest, the first element in the output list due to transitivity. So if 1 is less than 2, or rather, according to our comparator, 1 comes before 2. If 1 comes before 2, and we already know 2 comes before everything else in its list, because it's already sorted, then 1 must come, and 1 comes before everything in its list because it's already sorted. Or there was a tie. We have to mention the ties and how we break those ties arbitrarily. But since 1 is less than 2, and 2 is less than all these, and 1 is less than all these, we know that 1 is less than, or comes before, or at least is tied with all other elements in either list. So 1 comparison, and we effectively compared 1 with n different values. So 1 gets copied over, and we advance the pointer. 19 and 2, same thing. 2 comes before 19. Therefore, it comes before everything else that's after 19. And we already know that 2 comes before everything that's after 2 in its own list because these lists are already sorted based on whatever comparator we're using, less than in this case. 3 and 19, 4 and 19, 8 and 19. And then we reach the end of one of our lists. There's nothing else to compare. We have whatever's left in the first list in this case. Well, we know these values are already sorted, and there's nothing left to compare them to. We already know that 19 comes after everything in this list because we already compared 19 with the last element in that list. So we're just going to copy all those elements over without doing extra comparisons. Save ourselves a little bit of work. Doesn't matter asymptotically, but it can save us a little bit of effort. Copy all those elements over, and we have these merged, and we did O of n work. So O of n work, for each value that we copied into this list, we did at most one comparison. So if we have n elements total, we did at most n work. We have n runtime for this merge, and we get what we wanted. We get our n runtime for merging. Now we got our n log n runtime to be able to sort a list. So here's the code for merge. The code looks a little more complex than what it's actually doing, but there is some duplicate code whether we reach the end of the left list or the end of the right list, copying over the rest of the elements. And most of it is initializing these pointers, checking those pointers, advancing them if, depending on which one comes first, copying to the output list, and then advancing that pointer. And this is the only place where we actually use our comparator. There's only one place in our code where we actually call that comparator to figure out the order between left and right, is right here while we're merging two lists. That's the only place. We never actually used it in the merge sort call, only in the merge call in this method. And of course, we're using our type parameters. We were using our comparator from the merge sort call. When merge sort called merge, it passed along that comparator to that call of merge to be able to do that actual comparison to get the proper order that we want. And if we do some runtime tests here, I'm going to sort some values. Let's go right to it in the interest of time. Let's sort 200,000 values using Scala's built-in sort width. And then I have some timing code wrapped around this to see how long it's going to take to sort 200,000 elements. So let's run this. Compiling. It's going to take a while to compile. But it took significantly longer to compile than it actually takes to sort those lists. So less than 200 milliseconds, less than a fifth of a second to be able to sort 200,000 elements. 200,000 is a pretty small number when it comes to computers. And let's take a look. I got to check one thing real quick here. I changed this to merge. So this is the same code we saw in the slide. Split the list, or in the question in chat. This val left, right. This split at is actually going to return two lists. So that syntax is saying, I'm getting two return values, put the first return value in this variable I'm declaring named left, put the second return value in this variable I'm declaring named right. So if you want to return two values without creating a new class, that's how we do it in Scala. And then merge, same code we saw in the slides. Let's run this and see if we get close to 185 milliseconds. Oh. Yeah, we did, but I cheated. I should probably switch to my algorithm. It shocked me for a minute because we're not supposed to get anywhere close to that. We're supposed to be pretty slow at this point. So I don't even know if we'll get 200,000. I don't even know if we'll get there in any reasonable amount of time. So the built-in sorting methods, the punchline here, always use the built-in sorting methods. They are highly optimized over decades of lots of very talented engineers to be able to make sure that they are efficient as possible when sorting anything, any value that we can think of. But since and and they're hitting n log n. You can't do any better than n log n. It's theoretically impossible for comparison sort. But we can do okay. We still have an n log n algorithm, but my lists are really sloppy with this one. So I'm not using my lists the way I should be. So let me switch out my merge for this foreshadow merge, where I'm doing the same logic as merge, except I'm going to be more, going to be smarter about it in terms of how I handle my lists. And I'm actually going to use iterators for this and use my iterators to advance to the next element instead of creating brand new lists all the time and calling apply, which is going to be horribly wasteful. I'm going to use this foreshadow merge, foreshadowing the data structures part of the course, rerun this, and just getting rid of those issues with my linked lists without having to create new linked lists all the time, I'm doing okay. I mean, I'm not touching decades of engineers working to optimize the crap out of this algorithm, but my vanilla merge sort that you would see in any textbook is actually doing pretty good. I mean, it's a factor of 2, but it's not, you know, we were waiting for a while on that other one and it didn't even execute. That might have taken minutes. That's a huge factor. It's an asymptotic factor because of the list stuff that I'm doing is probably n squared log n of runtime with all my list lookup stuff, with being sloppy about that. But once I get rid of that inefficiency, I'm not that much worse than decades of engineers. They just spend a lot of time to optimize down to that lowest level, getting all of the optimizations they possibly can. But we're not doing too bad. So, and the next thing I want to look at, and the rest of what I want to talk about here, is how does recursion work? And how are we going to write our recursive methods? It will be the big focus, especially when we go back to the slides. So let's set a breakpoint here and shift gears to talking about this recursion explicitly. So we got, and I could run my selection sort, but it's going to be ridiculously slow. We don't really have to verify that. It's going to be horribly, horribly slow. So let's open up our debugger and see what's going on when we have this 200,000 random elements. I just generated random doubles here. So we have our list of a lot of random values here. We have our comparator. We can see, oh, how did I? We can see that our comparator, this actually is on the heap for what it's worth. Our functions are stored on the heap. It's actually of type function2, which is a Scala built-in type, which is a function that takes 2 parameters. The syntax will tell Scala how to create that object. And we can see that we're inside our main method call, where I'm just calling my large example, which creates the list and does the timing tests. And that's the one that's calling merge sort. So merge sort is the current frame that's on the stack. This top level merge sort call with an input of size apparently 200,001, apparently I have an extra 1 there. It's split this list into 2 lists of size 100,000 and 100,001. So we already got that split, and we're ready to make our first recursive call. So let's step into this thing. Make one recursive call. The length is not less than 2. Split this list. Our midpoint was 50,000. Oh man, it's taking a while to do it with this many elements. And then we get to our next recursive call. So we can start seeing our calls on the stack. Our first call to merge sort. The stack frame for that first call to merge sort is sitting right here waiting for that first recursive call to return. That recursive call just got to its first recursive call, and it's going to make a recursive call with a list of size 50,000, with those first 50,000 elements of this list. Then we can keep walking through this, but I'm going to set a different breakpoint. And I'm going to set a breakpoint when we get to our base case and then look at the frames that are on the stack at that point. So let's let this run and see what the state of the program is when we get to our base case. So we can see a lot more frames on the stack. We see our original call with 200,000, with a list of size 200,000, split it into 100,000 and 100,001. Our next call that we already saw with the input of size 100,000, splits that into 50,000 and 50,000. That made another call, got a list of size 50,000, split it into 25,000, 25,000. You get the idea. We have a lot more calls, keep splitting it in half, till we have a list of size 12, split it into 6 and 6. And all these are waiting for that first recursive call to return. Get another list of size 6, split it into 3 and 3. A list of size 3, split it into 1 and 2. And finally, we hit our breakpoint. We have a list of size 1. It is the list that contains just this one value, negative 0.44514 or whatever, in our comparator. And here we can start stepping through again. That's going to return. That's going to return our value. So we hit the end of this stack frame. This stack frame is going to return. And we're back to the stack frame 1 up from that. So we got this list of size 3. We split it into lists of size 1 and 2. We got our left sorted. So left sorted was just that list that was returned. And now we're ready to finally make our first recursive call on the right side of any of these values. We'll make this recursive call on the right side of size 2. That's going to split it into 2 lists of size 1, which are going to return and now we have right sorted. Oh, let me hit one more. And now for this recursive call, we got a list of size 2 with these 2 elements. We split them into 2 lists of size 1 and got our left sorted and right sorted. We got our 2 values. Now we're finally ready to call merge for the first time. We're going to merge these 2 lists. We're going to do all our pointer stuff, some good times. I'm going to skip through all this. It's not too interesting to look at 2 pointers, just looking at 1 element, 2 elements, I guess, and return that sorted list. So we've merged. So we successfully merged those 2 lists, and now we have our right sorted, and now we have a list of size 1 and a list of size 2. We're ready to merge these 2 lists together. Call merge, and start merging those. And this is going to start returning up the recursion as each one of these recursive calls start returning, start combining the lists from their return values, start making their recursive call to the right-hand side, getting that return, merging, making their recursive call to the right-hand side, returning, merging. Sometimes the right-hand side is going to make a lot more recursive calls to get its whole list sorted, but we can see all the calls being put on the stack, all these new stack frames, and then as those stack frames return, we're getting the functionality that we want out of this algorithm. And then, and we can see even with the last thing I want to point out, even with 200,000 elements, like we don't have all that many stacks on the frame. Like it's not frames on the stack. It's not a ridiculous number. This is our power of logarithms. As we're dividing that by 2 each time, just doesn't take all that long to divide, continuously divide by 2 to get 200,000 down to 1. Takes just this many recursive calls. Not many. Okay, so how do we write these things? How are we going to do that? Lecture question. Here's my suggested approach. Just like with the state pattern, I had my suggested approach. Generate your API, decide what states you need, decide what state transitions you need, and then figure out the functionality for each state for each API method. Similar to that, I have my suggested approach for writing recursive methods. First, write your entire method using recursion, and just assume that your recursive calls work. Assume that your recursive calls return the right value. Write your whole method based on this assumption. This might have something of the form of merge, where you make your recursive, where you do some setup, you make your recursive call or recursive calls, you get the return values, and then you combine those two recursive responses in some way. You might have some approach like that, which we call divide and conquer. But write your whole algorithm based on the assumption that your recursive calls work and that is fully functional, even though that is the method you're writing. It takes some bending of your mind to get that the first few times you do it. But just assume that they work. Then add in a base case, some really simple return value where you know the answer, and then make sure, very importantly, make sure your recursive calls are always getting closer to the base case. So in merge sort, we assumed that our recursive calls worked and wrote our entire top-level algorithm based on this assumption. So we have a list that we need to sort. We're going to divide our input in half, make our recursive calls, assume that those recursive calls work, and then merge those two recursive responses. Just merge two lists that are independently already sorted. Then we added in our base case. Okay, what's some trivial case where we can easily compute sorting a list? Well, if the list is size less than 2, just return it. That's my very simple base case. I know that I can sort that. So add that as what we call the base case, some condition where the output is trivial given the input. And then make recursive calls that get closer to the base case. Our base case is a length of 2. So our recursive calls are always making sure we're decreasing the length of the input. We get a length of size n. We're going to make 2 recursive calls of size n over 2. If we do this enough times, we're going to eventually reach our base case. And it's very important with recursion. We have to reach our base case. So our first 2 ones assume the recursive calls are correct and return the right value and write our method based on this. This is the really nice thing about recursion is it seems like the real work of a recursive method just kind of happens. We're just assuming it works, and then all of a sudden it works. It's a lot less load on our brains once we get used to the idea of recursion and get confident that it's working the way we want it to work. So this is where we see some of the advantage of recursion. If this is not correct, if we do something wrong elsewhere, well, that's something we got to fix. But write this algorithm based on that assumption. Just assume that it's going to work, and just go in there with confidence and write that method. Add in that base case with a trivial return value. This is typically empty list of size 1, as we saw. It's empty string, like we saw in the anagrams code that we'll talk about again on Friday. 0 or 1 usually has some trivial output. 1 for the lecture question has a trivial output. You just return it. You just return 1. So some base case where there's a trivial return value, and you just return that value. If you don't hit your base case, your else for that, if base case else, the else is your full algorithm with the recursive calls. So if you're not in your base case, this is the only time you're actually doing a real computation, which, if you can call it that, is your base case. That's the only time you're really just returning an answer, computing and returning an answer. Else, you're going to make the recursive calls and write your algorithm based on the recursive calls being correct. And then make sure your recursive calls always get you closer to that base case. If not, that's where you're hitting your infinite recursion and your stack overflow. If you see stack overflow in your code, which you're almost guaranteed to see at some point as we're using recursion. If you see stack overflow, you have infinite recursion. That means you're always making more and more recursive calls without hitting your base case. So the idea is that every call, you're getting closer and closer to your base case. Hey, you're asking a question. Am I at my base case? No. Make a recursive call to get me closer to my base case. And then in that recursive call, did I reach my base case yet? No. Okay, make another recursive call that's even closer to my base case. With merge sort, we kept splitting the list in half until we reached the base case, and then started merging the returns of our recursive calls together and started working with them. But if you don't hit your base case, if you have some recursive call that's just not making progress towards the base case or moving further away from it, you're going to get that Stack Overflow with that infinite recursion. It's like a loop that doesn't update your index that you're iterating over, where you have an infinite loop, which we don't, which I realize we're having discussions. We don't really see now that we just iterate over data structures. But if you have a while loop that just never is false, you have that infinite loop, you're going to have infinite recursion here if you don't reach your base case eventually. Because if you don't hit your base case, you are making another recursive call. If you're always making another recursive call, you just filled up the stack until you ran out of stack space. With stack frames, you have to reach that base case to stop the recursion and start returning and destroying stack frames instead of creating new stack frames and putting those on the stack. So if you're assuming your recursive calls are correct, you have a base case and your recursive calls always reach the base case, you got the formula for a good recursive method that's going to get you the solution you want without having to directly compute that solution by leveraging that recursion.